CS 402 on Wednesday, June 4th, 2014.
Either one is fine. Just sign this one. All right. So starting today, we are all right. The class has started. Hello, hello, hello. Yo, yo, yo. All right. The class has started. Okay. If you want to talk, please talk outside and come back in. Okay. All right. So starting today, we have the row sheet. If you come in late, don't just sit down. Come up and sign the row sheet first, and then sit down. Because later on, if you say, I forgot to sign it, I'm not going to allow you to sign it. All right, so sign it in the beginning. And please read the rule about signing the row sheet. If you are late, I think if you come into the class 10 minutes after the class has started, please make sure you check the late box. And if you have to leave, before 5 minutes before the class ends, please also, come and check the late box before you go. Okay, if you got a text or something like that and you have an emergency, you have to go, just go and then send me an email. Ask me to either erase your signature, from the row sheet, or check the late box. Okay, so this is the procedure, if you don't do that, if you don't follow the procedure, you come in late, you didn't check the late box, that's considered cheating, and you're going to lose all the 3% of the extra credit that you get for signing the row sheet. Okay, if you only miss one signature, it's only 1 out of 20, 1 out of the 20 signatures, so it's very, very minor. So make sure you don't cheat on these, very, very simple stuff. Okay, and same thing with, cheating and the programming assignment. I mean, in general, you just shouldn't take credit for things that you should not be, take credit for. And that's just having self-respect. Okay, so I really expect you to, you're a grad student, I expect you to do that. Hello, if you sign me, hello. If you come in late, please sign the row sheet right now, because later on you won't be allowed to sign it. All right? Okay, warm-up 1 is due at 11:45. Hello? Seriously, if you really want to talk, please go outside and talk and then come back in. Okay, the entire class can hear you talking. All right? All right, warm-up 1 is due 11:40. I mean, even though I'm talking about stuff that you know, please, okay, don't interrupt other, other people. Warm-up 1 is due this 11:45 this Thursday, and if you turn it in 1 day late, you get a 20% deduction. Again, read the class website for details. If you have code from a previous semester, be very careful not to copy from it. The best if you get rid of it. Okay, and you can start, warm-up 2 whenever you want. Read the lecture slide. I won't go over it, but read it. Read the spec. And if you have any kind of question, just send me an email, all right? Or start a discussion in the class Google group. For all the assignments, another reminder, the grading guideline is the only way we will grade, and we can only grade on Noonkey for the warm-up assignments, okay? So make sure you follow that. Make sure you have done the GDB exercise mentioned last week. You need to learn Unix, install Ubuntu 12.04, not the newer version, only 12.04, and start looking for kernel partners. So tomorrow I will record an extra lecture to make up for the holiday last Monday, and it's meant to be as a continuation of today's lecture. Okay, and I will assume that when you come to lecture next Monday, you would have finished watching that lecture that we'll record tomorrow. Okay, so I will continue picking up from the end of tomorrow's lecture. All right. Okay, so we are in chapter 2, talking about threads. Last time, we sort of almost finished here. I just want to have some more, clarification on this particular picture, right? We're talking about, a server, sort of your main thread starting 100, child threads. Okay, and every thread has its own stack, but they share everything else with the other threads, right? So they share the code segment, they share the data segment, which means global variables. They also share the heap. Okay, and they only have, separate stack. Okay. And also this picture says, you start with the main thread. The main thread is gonna, okay, the main thread, this is the main thread, right? Main thread is gonna call this function. Main somehow gets here, and then it's gonna create 100 threads. I'm assuming this guy is 100. Okay, so who's gonna run next, right? The idea over here is that we're gonna have 101 threads running in parallel. Who's gonna go next? When the main threads come, to the end of this particular function, are the 100 threads running already, or some of them are really haven't run yet? Okay, so what you need to think about this is that I don't know. See, I don't know is actually the right answer. Okay, if you know, then there's something wrong. Okay, you have to write your code to assume that you don't really know the order of execution of these threads. All right, even though you have a way to find out, maybe it will work on this particular machine, but it will work differently on the other machine. So do not count on it. Okay, if you look at some code on the internet to say, I want to set the thread priority so that I can make sure that the main thread has higher priority than all the child threads. Okay, then you got to make sure that all the child threads get to run at a later time, and setting priority is kind of a tricky thing. Okay, so I'm gonna ask you to stop yourself from using code that changes the priority of threads. Okay, try to learn how to make everything works without messing around with priorities. All right. Okay, so the other thing is that when you call pthread create, right? This is what I call the start function or the thread function of this particular thread. Okay, I think somebody pointed out that in the textbook it calls the first procedure. So they're all the same thing: the thread function, the first procedure. So in this case, it's referring to this function, right? And if you look at the function prototype of pthread create, where is that? Okay, so this function prototype, it has a strange notation. Okay, so basically, anytime you see something like this, that means that it's a function pointer. Okay, so over here we have a function pointer, right? Left paren star followed by right paren, and over here we just put a name in there to indicate sort of a default name for this particular variable. Okay, so this is the function pointer. This is the return type, is the stuff that before it, and after it are the arguments, for this particular function. Okay, so this notation over here is that here's a function pointer. It returns void star. We're all expert in void star now, right? And this one also take an argument, which is also void star. All right, so as you can see that in the example over here, the server function that we use over here matches that function prototype. It returns void star, and it takes one argument, void star. All right, so in this case, when you make pthread create call, what happens is that the child thread is going to get created, and this is going to be the start function of that child thread, or the first procedure of that child thread. Okay, and what happens is that this argument is also a void star. It's going to get copied directly over here. Okay, so over here it's a void star, copy onto a void star. It takes the value and just copy it over there. All right, and now this function is going to start running in the child thread, and they will take this thing as an argument, and they have to do something with the argument. All right. The final point I want to make is that all these threads, 101 threads, they share the same address space. Okay, you're going to have a thread. Let's say that this is one of the threads that's running. Okay, this is the stack, right? This is the current top of the stack, and here's the entire stack space. There's a limit. Is it okay for this thread to trash memory in another thread? Okay, so this is called memory corruption, right? When you modify a memory location that you don't intend to, or a memory location somehow get modified by whom, I don't know, but somehow the memory location is supposed to have a certain value, and now all of a sudden the value changed. I don't know who modified it. Okay, so that's a generic term that we use for memory corruption. Okay, so memory corruption doesn't mean that you have a physical piece of memory, some alpha particle from outer space, come and corrupt the memory. It means that your program modified the memory location. Okay, so is it okay for this thread that's using this stack to modify stuff over here? Okay, the answer is yes. Okay, because all the threads share the same address space, so any thread has the same write as any other threads. They can write all over the address space. Right? The definition of address space is their addressable memory. So therefore, if you can address this memory location, and if you're allowed to write to it, well, you can modify it. Okay, so this particular address space depends on the processor you use. Some of the processor will actually say over here you have the program down here. The program segment is actually protected. If you try to write to it, you're gonna trap into the operating system. Okay, some operating system might not do that. You can even write to the the code segment over here and modify data. So therefore, any one of these threads can write data all over the place. As long as you have the address for that memory location, you can go ahead and put data there. All right? Is this very dangerous? Of course, right? But it's also very powerful. So you can actually have one thread modifying data for another thread. All right? So be careful, with this. Okay, and last time we talked about, these, by the way, I think last time I wasn't very clear about one thing. It's about this guy. Okay, I said that this might be the thread control block, and then I corrected myself, said, maybe it's just a thread ID. Okay, as it turns out, it is a thread ID. So this is I think on Nunki, you will see that this is really a large number, like a 64-bit ID for this particular thread. Okay, it's not the thread control block because I also mentioned that, the thread can be implemented in the kernel or in user space. So if it's in the kernel, you shouldn't really have, access to something in the kernel. Okay, so that's why it wouldn't make sense that this thread is actually the thread control block. All right, so this thread, this return value over here of the type pthread_t, that's just the thread ID. Okay, some code that you will see will actually call this thid for the thread ID or TID or something like that to indicate that it's just an identifier. Okay, so over here we call it a thread, but it's just an identifier. All right? Okay, the last time we were at this this slide, and this slide has a gray X on the lower left corner, and a lot of the Windows stuff we're going to skip. All right, so over here, we go back to the code for the remote login daemon, right? We mentioned that the remote login daemon is going to create two threads. One is called the incoming thread, one is called the outgoing thread. And every thread will actually take two arguments. Okay, so over here, it does a no-no, right? It says pthread create, the incoming thread, and it passed two parameters to it. Okay, so when you try to compile this, you're going to get a compiler error because, pthread create only take 4 arguments, so you can't really, take 5 arguments. Okay, so this doesn't work and this doesn't work. Okay, so we got to make something to make it work. And also, there's the other thing is that, this function, when it finishes creating these two threads, it will return. Okay, so basically this particular function will return. And we mentioned before, right, that when you run a function when you call a function like this in the main thread, what's going to be on the program stack? Okay, what's going to be on the stack, right? These function arguments is going to be on the stack frame for all login, and also the local variable is going to be in the stack frame. Okay, so as soon as this function return, all these things become invalid. If they become invalid, and if you pass it to another thread, then you got to be very careful. Okay, because if they are actual value, the value get copied, like I said before. Okay, they get copied into the argument. So if they're integers, then they're fine. But if they are pointers, then you got to make sure that the pointer points to valid memory. All right, so we're going to come to another picture, which might make that point a little clearer. Okay, so if you can't, if you can't pass multiple arguments, so what should you do? I mean, in C, you just create another data structure that has two things in them, and then you pass that data structure. But in this case, the data structure might have multiple things in them, so you really cannot pass the entire structure, so you have to pass the address of that data structure, right? So therefore, what you can do over here is that I can define a data structure type that has two things in them. The first thing is called first, the second one is called second. And in this case, we're going to call pthread create for the incoming thread. I will pass the address of in, and in is a local variable over here of this type that I just declare over here. And it has two things. These are the two things I want to pass to the child thread. Okay, so this is how I can pass multiple things into the child thread using only a single data structure. Okay, and over here I use the address over here, so it's kind of like void start, right? So you take the address and you copy into this guy. So this case, arg will be here, will be just the address of in. Okay, so it's going to be, the address of IN is a 32-bit quantity, which is an address that points to this memory location. Okay, so inside this code, what I need to do is that I need to typecast this one to the right type and start getting the data, the RE and the L out of this argument. Okay, so in a more detailed picture, it looks like this. Okay, so if this one is invoked by the main thread, right? So inside the stack of the main thread, this is the stack of the main thread. Okay, so it started out with the main function. The main function is going to call something, it's going to call something. Eventually, it's going to call rlogin_d. So you have a stack frame for rlogin_d right here. Okay, inside the stack frame lives the function argument and the local variable, right? So this guy, this guy, this guy, this guy are somewhere in here. And then finally over here, there's a two variable in and out. So the in and out, they live right here. Okay, each one of them, how big are these data structures? This one data structure is 2 integers, so they are 8 bytes long. So over here, there are 8 bytes right here, and there are 8 bytes right here. Okay? And then when you call pthread create, you create a child thread, you get a new stack for the child. Okay, so the child thread is going to be right here. Its first procedure or the start function is going to be incoming, right? So in this particular stack, the first function is going to be incoming. And then there are, what's there? There's arg, and then there's p. Okay, so arg is somewhere right here inside the stack frame, and p is also inside the stack frame. When you create this, you copy the address of int. The address of int is this guy, right into the arg, and then the first thing over here is you copy arg into p. All right, so think about these things. These are just 32-bit integer value that you're copying, right? So the address of int eventually is going to end up in this memory location. Okay, so what happens is that you can interpret this one as this is the pointer that points to this address. Okay, so that's all that happened when you copy these, address of a variable from one place to another. And again, this is why I want you to go through that GDB exercise. So when you try to run this particular code, you can actually set a breakpoint in this particular function. When you break over here, you can actually print p and look at the content of p, and it should be the same content as the address of the in variable in the parent thread. All right, so you got to start getting used to this. Set a debugger, break right here, and examine this memory location to make sense out of it, to make sure that you understand what the values means and why are some of the addresses small and why are some of the addresses large. Okay, global variable has small addresses. Stack variables has large addresses. Okay, so you can use that as a hint to tell you where these variables live. Okay? All right, so this is how you pass from the main thread to the child thread. Okay? So now there are many different options, right? You can pass the address of a local variable, you can pass an address of a global variable, you can pass, some pointer into the heap. Okay, so you got to keep track of where these things are, right? The local variable in C and C++, they'll have another name. They're called automatic variables, right? They are automatically allocated, and they're also automatically deallocated. Okay, and they're automatically allocated when the function is called. They're automatically deallocated when the function is returned. Okay, so these variables have a lifetime because these variables live in the stack, right? Again, function arguments, local variable live in the stack. They are local variables, they are automatic variables, they are stack variables. Okay, so as soon as the function returns, these things become invalid. So you better not have a pointer point to that stack over here, stack over there. Right? If we go back to the previous picture over here, okay, if our login_d return, okay, then this memory location becomes garbage, because what happens is that when you return from our login_d, that means that the main thread is executing. It's going to go back to the previous function. The previous function may call another function. When it calls another function, it's going to build the stack frame right on top of it and wipe out everything that's over here. Okay, so therefore, once you return from our login_d over here, then you can no longer count on the value over here being valid. Okay, so be very careful when you do that. Okay, and you say, well, then if I want to avoid this problem, I'm going to use global variables, right? Because the global variable, they will always be there because they're in the data segment. All right, but there's only the problem with global variable is that remember when we talk about Turing machine, is that the global variable you have to name all of them. You have to give every one of them names. Okay, that might be a problem. Maybe there are things that you don't really have names for them. Okay, or you have a recursive function, the same variable you want to use it at different time, meaning different things. Okay, so you can't really go with naming everything. All right, so you end up putting stuff in the heap, putting stuff in the stack. You need to be responsible of keeping track of all this thing in your head to make sure that they actually work properly. They have a little note over here. You need to ask yourself, when you write your code, you say, how do I make sure that this variable points to the right place? Okay, when this function returns, everything still points to the right place. Okay, and those memory are valid. Okay, if your answer is, I hope it works, that's not the right way to go. Okay, you got to make sure that you are sure that that memory is going to be there. All right, because otherwise, when you start doing warm-up 2, you're going to have memory corruption problem left and right because, you're writing to memory location where you're not supposed to. All right? Okay, so in order for this rlogin not to return, okay, so one thing we can do is that we can wait for the child thread to finish. Okay, so over here, right, what we can do over here is that we create these two child threads, okay, and then we pass them the address of in and out, right? So if this function returns, then the child thread is going to be in trouble because whatever data they're accessing might be invalid. Okay, the child thread might not even be started when this function returns. Okay, because you have no control of when the child thread gets started, and you don't want to control it. Okay, so therefore, what you're supposed to do is that, what if you do this over here? Is that basically just like processes you can call wait. I say I want to wait for the child thread to die. Okay, so the way in pthread to wait for the child thread to die is that you call pthread join, right? Pthread join takes two arguments. The first argument is the thread ID. You say, I want to wait for this thread, the in thread right here. Okay? And the second argument is the return value. Right? Remember in wait, return two things. One is the process ID of the child, and the second one is the return value of that process. Okay? So over here is the same thing. But in this case, you have the thread ID of the thread that you're waiting for. So all you want is getting the return value. Over here, you pass a no pointer over here, says I'm not interested in the return value. Okay, so this function will not return until this thread dies. Okay, if this thread dies, has it done using the in variable? Of course, right? The thread is dead, right? So therefore, you can free up this memory location. It's okay for the function to return. Okay, later on, you call pthread create the output, the outgoing thread, and over here you wait for it to die. When it dies, that means that it's completely done with the out variable. So only at this point you can return from rlogin d, and then these memory locations become garbage, and that's perfectly fine because I'm done using them already. All right. Okay. So pthread join is the way that you wait for a thread to die, and so as it turns out in processes, the processes has parents and child relationship. Okay, in threads, there's actually no such relationship, right? Even though I'm calling it parent thread and child thread because it's easier to talk about. The parent thread, create the child thread. But once you do that, any thread can wait for any other thread to die. Okay, the child thread can actually wait for the parent thread to die. Okay, because after that, there's really no parent and child relationship. Okay, or as long as you have the thread ID, then you can wait for it. The return value over here, the type is voice star star, right? So what is voice star star? Right, voice star star is voice star, right? And then this one has another star, right? It's a pointer to something, and this something just happened to be a pointer to another thing. All right, and in warm-up 1, a pointer to something, it doesn't really mean anything. It doesn't really have to be a pointer. It can be anything, right? So what this means is that on a 32-bit machine, this is the 32-bit quantity, and the way you can interpret it is that it points to a memory location that has another 32-bit quantity, which might be a pointer, which might not be a pointer. All right, so again, anything can happen. So here's an example where the child will pass a return code to the parent, okay? And the way that you pass the return code is to, to either call return in the start routine, okay? Or you can call another function called pthread exit, okay? So how does a thread self-terminate? A thread self-terminate in two ways, right? So this is any one of the threads if they want to terminate, right? Either it go return from the start routine, you have to execute a return statement, okay? The return statement, you can pass an argument over here, okay? The argument has to be of type voice star, and of course you can typecast integer to voice star, whatever you want, okay? And this one will be copied into the thread control block, okay? So the thread control block has a thread ID, has a return code, so this value will get copied into the return code, okay? And then another thread, when they call pthread join, that return code is going to be copied into the arguments in pthread join. All right? So this is one way to die, and the other way is to call pthread exit. Pthread exit, you can give it a return value, and this one will also terminate that thread. Okay, so this is called self-termination because the thread is executing this code to terminate itself. Okay, there's also a way for one thread to kill another thread, but that's a different thing. Okay, so if you want to call pthread exit, then pthread exit take one argument, and that's the return value. Okay, here's an example of the child thread. Okay, it has tried to return, try to self-terminate in two ways. One is normal termination, right? You execute the last statement of the start function, and it called return something. In this case, it return 2. So the meaning of 2, meaning that it's normal termination. Okay, in this example, right? The other one, it says, if it's executing some code to determine that it should terminate right now, it might call pthread exit with void star of 1. Okay, this can also be replaced with return void star of 1. Okay, that would be the same thing. Okay, the main difference between pthread exit and return is that, in this example, there's no difference. Okay, but if you imagine that, this child, start routine calls another function, and that function calls another function, and calls another function, etc. Way down in here, you decide that this thread needs to terminate. Okay, if you want to do return, you have to return here, return here, return here, and that's really cumbersome. One thing that over here, you can just call pthread exit, right? Okay, and then the thread will terminate with the return code. All right, so that's the main difference. You can use pthread exit anywhere in any of the function of that thread. Okay, if you're going to only use return at the start routine. Okay, so in this case, the parent thread, right, they call pthread create the child, doesn't really pass any arguments over here. Okay, and then it can wait for the child to die. It says pthread join thread is obtained over here. Okay, and then what it will do is that it needs a return code, right? Okay, so the return code, the function prototype says it needs to be void star star. So there can be an address of a void star, variable. Okay, so over here we declare a variable void star result. Okay, so this one basically says it's a pointer type. It's a 32-bit on a 32-bit machine. Okay, it's uninitialized right here. I'm going to pass the address of result into this argument. Okay, so when the child thread dies, the pthread routine is going to copy the return value into this memory location. So that would be the same thing as setting result equals to 1 or 2. All right, so again, this picture, right, in the parent thread over here, you call parent right here. Result is a local variable over here, and it's 4 bytes long. Okay, when you call pthread exit, you give the address of this one to pthread's library, and the pthread library will copy the return code into that memory location. Okay, and that particular memory location comes from this. When you call pthread exit, the number 1 or 2 get put into the thread control block of this particular thread. Right, inside the thread control block, there's the thread ID. Okay, there's also the return code. So if you put 1 in here, then the return code is going to be equal to 1. And over here, when you call pthread join, 1 is going to be copied into the result location. Okay, so when this guy returns, you can do a switch on the result value to see if it's equal to 1 or 2. And then you know how does the child thread terminate. Is it normal termination or is it terminate now? All right? Okay, and the thread can only return one thing. And turns out this is the pointer type. So if you want to return some kind of a data structure, you should allocate that data structure in the heap, right? Okay, or you have that data structure in the global variable, you can write into the global variable. But if this one is something, if you return a pointer into the stack right here, into a local variable over here, then you're going to be in trouble, right? Because when the thread terminates, this entire stack is gone. So you better not point to and have a pointer that points to somewhere inside the stack frame, because that will be invalid. All right? And also, again, thread termination, all these threads, the parent and the child thread, when the child terminates, okay, it's going to keep the thread ID and the return code around. Okay, just like when process go into a zombie state, you can say that the thread also go into the zombie state, waiting for the parent to call pthread join. When the parent call pthread join, that's when it fetches the return code, and then this thing can get destroyed. All right, but if the return code is a pointer pointing to the stack frame, then you're going to be in trouble, right? Because later on, this thing will be gone, and you'll be reading garbage from the stack. All right? Okay, the difference between pthread exit and exit. Pthread exit only terminate the current running thread. right? So pthread exit is called by the thread, right? So there, if you think about a single processor, only one thread is executing at a time. The one that's called pthread exit, that's the thread that gets terminated. Okay? If you call exit terminate the entire process, including all the threads that are running in it. Okay? So therefore, if you have a code that looks like this, I have a main code. Over here, I'm going to call my previous code to create 100 thread. Okay? And the main thread calls return 0. Okay? So what happens when you call return 0? Well, when you call return 0, so the main function, where does it return to? So it turns out it returns to another function, right? That's what return means. Okay, so in the main thread, right, I've been drawing the picture that main is the first function. Okay, so it turns out that's a lie. Main is really not its first function. There's actually another function that's before it, right? So this is called the startup function. Okay, so before main, there's a startup function. Okay, all the startup function is doing is that it will get the return code and it will call exit. All right, so over here in the starter routine, when it returns 0, then basically we'll call exit 0. So therefore, you will kill the entire process, right, because you call exit. Okay, so that means that all the other threads, whether they're running or not, they all cease to exist at that point because all these things will be cleaned up. The only thing that's left in this process is going to be the process ID and the return value. Okay, so that's the major difference between pthread exit and exit. Okay, so in this case, what happened is that when you call return 0, you call exit right away. Has any of these threads started to run? Right, the correct answer is, I don't know. Right, maybe some of them has been running, some of them hasn't been running, maybe none of them has running, maybe all of them has finished. I have no idea. Okay, so this is really not a good way to go. Okay, unless this is really what you want. Okay, if this is what you want, then go ahead, right? But normally what you really want is that if you really create a bunch of threads, you really want to wait for those threads to finish. So what you will do is that before you go return 0, you wait for all those threads to join so that they all finish what they're supposed to be doing, and then only at that point, you can exit the process. What about this, right? If you call pthread exit right here, instead of calling exit, right, you call pthread exit. Okay, now, so in this code right here, commented out, right, you create 100 threads. So now it's possible you have 101 threads all running. Okay, if you call pthread exit, what happened? If you call pthread exit, then your main thread is dead. Okay, does it kill the program? No, right? You only kill one thread, right? All the other threads are running. So eventually they all get their chance to run. They run and run and run. And then all of them finish. What's wrong with that? Okay, so what's wrong with that is actually nobody call exit. Okay, if nobody call exit, what about the parent thread? If the parent what about the parent process? If the parent process is waiting for this child to die, then this child never dies because the child never call exit. Right? I mean, the definition of wait is that you're waiting for the child process to die. If the child process never actually dead, it only goes dead when they call exit. Okay, and now the parent process will basically waiting for a zombie forever. Okay, so that's really bad. Okay, as it turns out that this is a special case. pthread library, when they implement it, they actually notice that that this is actually a bad condition. So they actually do some kind of a reference counting. So when this process, when all the threads all call pthread exit, they say, oh, okay, well, we got to call exit for this process because otherwise it never becomes a zombie and the parent can never finish. Okay, so therefore, pthread actually take care of it in this case. Okay, but so you can do your code this way. Really, although this is really not a clean way to go, you're counting on the behavior of pthread library to do the right things for you. The real thing what you're supposed to do is you call, instead of calling pthread exit over here, you should call a bunch of pthread join. Wait for all the child thread to die before eventually call exit. All right, that's the right way to code. Okay. By the way. All right, over here it talks about the zombie state for the thread, very similar to processes. You can also detach a thread. Okay, so over here, what you can do is that you can create a thread. Okay, and then you say that I don't want to join with this thread. If you don't want to join with the thread, you actually have to declare it explicitly, say I will never want to join with this thread. So therefore, you call pthread detach this particular thread. So when this thread, this child thread dies, it will not go into a zombie state. All right, because otherwise, when a child thread dies, it will go into a zombie state. This one says, I don't care about this thread. I never want to know its return code. So, if it dies, just kill it. Okay, free up the thread ID data structure because I'm not interested in it. All right, so that's one way to do it. Okay, but again, in our programming assignment, you should try to wait for all your child to finish by calling pthread join. Don't try to detach the threads. All right, so the third argument over here, this is a function pointer. Okay, so again, the function pointer, what is a function pointer anyways? I mean, in warm-up number 1, you saw the header file, there's a bunch of function pointer, right? The function pointer is just a pointer. It's just the same thing as a pointer to voice star. It's just a pointer to integer, a pointer to anything. A pointer is just a pointer, right? So actually in C, a pointer is just a symbol, okay? Or a function is also just a symbol, right? It has, if you think about what address space look like, okay, here is the code segment, okay, and over here you have a function called foo over here, right? Okay, foo, what is foo? Foo is just an address. Okay, so a function is nothing more than just an address. It just happened that at this particular memory address, there's a bunch of code there, so you want to point EIP to that particular memory location and start executing code. Okay, that pointer is no different than any other pointer pointing to data segment, stack segment, or the heap. Okay, so this argument, you can actually give it anything you want. You can give it a, give it an integer, it's compatible. You can give it a function that's of the wrong prototype, that's also fine. Okay, you can also give it something that's correct, so make sure you pass it something correct. All right, compiler is not going to complain if you just do typecasting. If you typecast the right way, it's just a 32-bit quantity, and they're all compatible. Okay, so be careful. Thread attribute are usually not used, but you can use that to specify a stack size. Okay, so over here, if you want, for some reason, you want a larger stack or a smaller stack. So so if you want to create 1,000 thread, then maybe every thread had to have a small stack. Okay, so why would a thread need a large stack? I mean, if you think about the function that you implement in warm-up number 1, right, starting from main call something, how deep does the stack grow? Not very much, right? Okay, so most thread only needs a tiny stack. Okay, when does it need a big stack, right? I mean, of course, if you create some very, very large variable, local variable inside the function that you're going to call, yeah, then it's going to take up, sort of a large stack frame. Okay, but usually the stack are pretty small, right? If you want to write a recursive function, okay, then potentially it can get very large, right? Because you have a function calling itself, so you start using up a lot of the stack space. Okay, so if you know that you're writing a recursive function, maybe you want to change the stack to be large. Okay, if most of your thread is small, maybe you can control your stack to be smaller. Most of the time, we're going to just use default because 32-bit address space is really, really large, so you don't really have to manage it explicitly. Okay, but if you really have to control it, you can actually do it. All right, here's an example of using multiple threads that will actually help when you have multiple processor. This example is doing a matrix multiplication, right? You have two matrices, A times B is equal to C, right? A is a matrix, B is a matrix, it's equal to C is a matrix, right? So the entry over here is this row times this column, whatever. Okay, so what you can do is you can do divide and conquer, right? You take this matrix, you divide it into 9 parts, and then you have one thread working in this area, one thread working in this area, so you can actually have this program run 9 times as fast. Okay, so in this case, that's because the thread don't have any dependencies, so therefore you can actually have them run on 9 different processors, and then you're going to run 9 times as fast. Okay, usually we're not that lucky because the thread actually depends on each other. Okay. All right, so here's an example program. You can actually compile it, and then you're going to link it with the pthreads library. So over here, I use -l pthread, and I guess also there's another notation. It's just a -pthread without the L. Okay, either one should work. All right, so if you forget to do this, this is the link step where you try to take the code in the pthread library and put it into the code segment of your, of your executable program. If you forget to do that, you're going to get error messages. Okay, so when you do warm-up 2, when you try to compile your code, in the last step, when you try to link and you get symbol not defined, pthread create, then it's probably because you forgot to do this. Okay. All right, so that's the quick introduction to threads, okay? And now we're going to talk about what if the threads going to run into each other, okay? They're going to, step on other threads' toes. Then the terminology that we use is we're going to call this thing synchronization, okay? We're going to have two threads, one thread over here. Okay, so this is a thread, here's another thread. They're executing, and they are sharing a memory location that they both want to read and write from this memory location. Okay, so how do you do it? Right? If I don't synchronize access to the shared memory location, and where is the shared memory location? It's anywhere in the address space, right? Because these two threads belong to the same process. This is any memory location in the stack, in the heap, in the in the global in the data segment. Okay, so any kind of a memory location that's going to be shared by two threads, then you got to make sure that they don't write and read this location at the same time. Okay, so that's called synchronization. You're going to have this guy access it first. When this guy is done, then you have the other guy access it. Okay, it's very important because otherwise disaster can happen. The textbook actually have this funny picture in there to explain synchronization. So this one is called mutual exclusion. The idea is the same thing. You have a memory location. Two guys want to access it at the same time. Okay, if you don't try mutual exclusion, meaning that both of them cannot access that at the same time. Okay, what happens if you access it at the same time, right? So here's an example. This is like the First World War, some airplane. You have a machine gun that's sitting right here. Oops. Okay, here's the machine gun, right? It's firing bullets, and here's the propeller. Okay, if you don't synchronize them, what's going to happen, right? You're going to shoot bullets into your own propeller, and then you're going to go down. Okay, so therefore, even in World War I, they know that they have to do mutual exclusion. As the propeller comes into the front, if you hold on to the trigger, the bullet's not going to fire. Okay, so that's mutual exclusion, right? So now that's what's done in hardware. Now we're going to do things in software. Okay, I mean, this is like a operating system crash, right? Okay, so now we have two threads. There's a global variable called x, okay, and both of them try to access it. Thread 1 says x equal to x plus 1. Thread 2 says x equal to x plus 1. Okay, is that a problem? Okay, so this is the increment operation, right? So what are the possible execution sequence, right? You have to, you only have a single CPU. Okay, you can only execute one thread at a time. Okay, so it looks like this shouldn't matter, right? Because what happens is that we can run this thread. Okay, x equal to x plus 1, so let's say x equal to 5 before. Okay, when you run this thread, it's going to be increment equal to 6. And later on, you run this guy, it becomes 7. That's correct. Okay, or x equal to 5, you're going to run this thread first. Okay, when this guy's finished, x equal to 6, and then this guy is going to execute, is equal to 7. So it's also correct. Is there any way for these two threads to be interleaved in a funny way so that x gets to the wrong value? Okay, as it turns out that it's actually the case, right? And the reason is that this is not machine instruction. Our CPU execute machine instructions. Okay, the CPU doesn't execute these high-level instructions. Okay, so it is possible that in the middle of executing this instruction, you might switch to execute another thread. Okay, so in reality, okay, if you look at the compiler-generated code, you will see assembly language or machine code that looks like this. X equal to x plus 1 becomes 3 instruction. It says LD R1X, add R11, ST R1X. Okay? And over here, thread 2, the code is exactly the same because it's the same code. Okay? If you look at, physically what happened is that this is the CPU sitting right here, and this is the memory, right? X is going to be sitting in memory somewhere. So X is actually not inside the CPU. X is actually somewhere else. Okay? So X is right here. Okay? Here's a memory location called X. We have the number 5 in it. Okay? And, this processor is connected to memory using the bus, as I mentioned before. Okay? So now this instruction, LD, so there's no way for this processor to say, go to this memory location and increment by 1. Okay? That's not how processor works. It cannot do that. Okay? So it's going to do something like this. Load R1X. R1 is one of the general purpose register inside the CPU. So R1 is actually sitting right inside here. Okay, so it's going to read memory location X. It's going to generate a read cycle on the memory bus, okay, or on the system bus. Take the content of X into here. So now R1 is equal to 5. Okay, the next instruction is add R1 by 1. So R1 is now equal to 6 inside the processor. And the last instruction is store R1X. is going to take R1 and copy into this memory location. It's going to become 6. Okay, that's how x equal to x plus 1 work. Okay, thread 2 is going to do exactly the same thing. Okay, so now the problem is that what happened is that if you do load R1 into X, okay, and then for some reason you switch to thread 2. Okay, so what's going to happen in that case, right? So if we follow this, okay, so we're right here, right? You load R1 with X, okay, and now you swap out the context. This entire CPU state is written into the thread control block of the thread 1, right? This is thread 1's thread control block, okay? And then you run thread 2, TCB of thread 2, okay? You load this guy into the CPU and start running, and you end up running this code. Okay, this code is going to do the same thing, load R1 with X, right? So X, what is X? X is still 5. That's the problem, right? 5 is going to go in here, into R1 over here, increment by 1 becomes 6, write it out here, this location becomes 6. Okay, and then this thread will do something, eventually it give up the CPU. This thread starts to run again. This thing is going to go restored from the thread control block. The content is going to get restored into the CPU. When it go restored into the CPU, R1 is equal to 5. Okay, when you restore stuff, everything go back to exactly the instance when that thread gave up the CPU. Okay, that thread gave up the CPU right here. So R1 is equal to 5. And the EIP is going to point to this instruction. That's the next instruction to execute. Okay? So when thread number 1 execute again, R1 is equal to 5. The next instruction is add R1 equal to 1. So this one becomes 6. Okay? Store R1 into X. This guy, 6, get overwritten by 6 again. Okay? Is that a problem? Right? The problem is that both thread 1 and thread 2 thinks that they have incremented X by 1. So X should be 7 now. But instead, X is still 6. All right, so this execution is incorrect. Okay, and this execution is incorrect. Is it incorrect every time? No, it's because you were unlucky, right? You were, when you execute this instruction, it's a bad time, and you got switched out of your processor. Okay, your context gets saved, and you run another thread. If you switch out right here, or if you switch out right before that, then X is going to be correct. But just because of the bad timing, you're going to end up with the wrong result. Okay? So if your execution, if the result of your program depends on the timing of execution, this is usually known as a race condition. Okay? You have two threads racing to do the same thing, and turns out depending on who gets there first, or how things are interleaved, you get a different result. Okay? So the general term is race condition. All right? So this race condition is going to cause your program to behave incorrectly, unless this is actually the intention of your program, which will be pretty weird. Okay? So what you need to do is over here is that thread 1 and thread 2, if both of these threads want to increment X, you need to synchronize the access to memory location X. All right? Then they will, they will always do something that's predictable. All right? You should not have race condition in your code, because then the execution of your program depends on the timing. Okay? Another possibility over here is that thread 2 will execute in another processor. Here's CPU 2 sitting right here. Okay? So thread 1 will execute these 3 instructions. Thread 2 will execute CPU 2 simultaneously. Right? So what happens is that this guy will load X into R1 in CPU 1. This guy will load the number 5 into R1 of CPU 2. Both of them will increment it in their own processor to 6, and both of them will write to that location. Can these two processors write to this memory location simultaneously? They can't, right? Because they have to wait. They have to access the bus. The bus only allows one thing to write to memory at a time. Okay, so this guy is going to write 6 to it first, and then this guy is going to write 6 to it later. Okay, or the other way around, doesn't matter. The end result is the same. The memory location is going to have the value 6 in it. All right. Again, this won't happen every time. Right? It just so happened that both these two CPUs are executing this code simultaneously. That's why you end up with this race condition. Okay? If they execute at a different time, then the result is actually going to look correct. Okay? All right. So how do you synchronize it? Okay? So the idea is very simple. It's kind of like, if you have a safe. Okay? So it's kind of like having a safe deposit box. Okay? So you have a safe deposit box. Okay, and if you have stuff that you want to, you have something important document, you only want one person to access it at a time. Okay, so what we're going to do the following. We have a safe deposit box. We'll actually put the key right on top of it. All right, there's only one pair, one key. Anybody who wants to access the document inside, grab the key, open the safe, take the document, write it, modify it or read it or something like that. When you're done, put it back in the safe, close the safe, and put the key back. Okay, is there any way for two people to have access to the document simultaneously? No, right? Because they have to grab the key first, and there's only one key. Okay, so it's very, very simple, right? Is that you have a key over here. In order for you to access the shared thing, you have to be in possession of the key. Okay, so how do you make so now the key becomes the shared thing? How do you make sure that you access the key in a mutually exclusive fashion, right? So we need some kind of a programming primitive to make sure that we can access to something mutually exclusively. All right. So what we end up doing is that we use something called a mutex. Okay, or sometimes we're going to call this thing a lock. Okay, so this, actually in this picture it looks like a key, but we're actually going to call it a lock. Okay, so what you need to do is you need to obtain the lock first. Once you obtain the lock, you can access the variable that are being shared. Okay, and when you're finished accessing it, you're going to return the lock, or you're going to unlock. And once you unlock it, you promise not to touch the variable. Okay, can you go ahead and touch the variable anyways? Okay, you could, but you're going to end up with race condition. Okay, so you only do this if you want to avoid race condition. And of course, you want to avoid race condition because you want your program to have predictable results. All right, so therefore, if you want your program to have predictable results, you got to make sure that you use these mutex or locks when you try to access shared variables. Okay, so here is in pthreads the mutex of the type pthread mutex type. Okay, over here we can initialize it using this particular syntax, and now we have a variable x that's being shared. Okay, in order for us to access x, we're going to say that, well, if you want to read or write memory location x, you got to make sure you obtain the mutex. Okay, the way that you can lock the mutex is to call pthread mutex lock, and you give the address of the mutex variable. This function, when it returns, okay, so this function, if you don't have the lock because somebody else is using it, this function will block forever. All right, so this is the blocking call. You call this one, somebody using it, you just wait forever. Your thread is suspended. Okay, when this function returns, that means that your thread has the lock. Okay, so the pthread library will enforce this particular meaning is that, if pthread mutex lock return, this thread has the lock. Okay, once it has the lock, I'm going to go into this section. I'll call it the critical section. The critical section is the place where you're allowed to read or write memory location x. Okay, so in this case, I'm associating this mutex with this shared variable x. Okay, so if you want to access memory location x, you have to make sure you lock the mutex. Okay, only when you lock the mutex, and the only way that you can make sure you have the mutex locked is that you have to wait for pthread mutex lock to return. When it returns, you have the mutex, so you can go and do anything with x that you want. Okay, I mean, in general, x doesn't have to be an x. X could be a linked list, could be a large data structure, or it could be whatever, right? Only when you got the mutex locked, then you can do anything you want with this particular variable. Okay, and when you're completely done with it, right, this is a linked list, you can add stuff to it, you can delete stuff to it. When you are in the critical section, the linked list may go out of whack for a while, but eventually it needs to be in a good state, and that's when you're allowed to unlock the mutex. Okay, if you're modifying linked list in the middle, if you unlock the mutex, that means somebody else can access the mutex. If the linked list is in a broken state, then the other thread is going to crash. All right, so therefore you only call pthread mutex lock when you're completely done with the shared variable. All right, so this is the basic protocol. Okay, all right, I'm going to read this a little bit. Code between mutex lock and mutex unlock for a particular mutex is called the critical section with respect to that particular mutex. Okay, every critical section is going to be associated with a particular mutex, and that particular mutex is also associated with either one variable or a bunch of variables. Okay, for mutex, the operating system, well, actually, it doesn't really have to be the operating system. Who is implementing pthreads library, okay, that's the entity to guarantee that only one critical section can be executing at any point in time. Okay, so if you only use one mutex to protect, a bunch of variables, then, if you follow this particular convention, then there's only one thread that are executing in a critical section, and that's the thread with the mutex locked. Okay, all the other threads, they're all waiting for the mutex to be unlocked so they can start grabbing that key on top of the safe. All right? So all the critical sections with respect to a particular mutex are therefore, right, given this definition, they're all mutually exclusive, okay, because only one critical section can be executed at a time. All right? So this kind of stuff can actually be done either in the kernel or in user space. So we're actually going to show you how things are implemented in chapter 5. Okay? For now, for pthread, you should think about pthread as a user thread library. Okay, we're going to write user level code, and the user level code, we're going to call pthread mutex lock and unlock in order to get into critical section to modify certain variables. All right? Okay, so you can initialize the mutex by doing something like this, if it's static, okay, or if it's a stack variable, okay. But if it's something in the heap, if you malloc a mutex, in that case you have to initialize it by calling this particular function. Okay, if you dynamically allocate a mutex before you free it, you should also call mutex destroy. Okay, but if it's a static one, then you don't have to do anything to it. All right, and usually the mutex attribute are not being used. All right, so when we have a single mutex, then it's fairly straightforward. Okay, you're not going to get into any kind of trouble. But usually, any kind of a complicated program that we write, we're going to end up with multiple mutexes. Okay, then things can get a little weird. Okay, so mutex is not a cure-all. When you have mutex, you're going to actually deal with the mutex problem. Okay, and the mutex problem are something you've probably heard of already. It's called deadlock. Okay, when you have multiple mutex that you're using, you got to use it very, very carefully. Otherwise, your program will get stuck and not make any progress. Okay, when you have more than one locks, you got to be careful. Right, here's an example. Here is procedure 1. It's called by thread 1, and here's procedure 2 called by thread 2. Okay, in procedure 1. You lock the first mutex, and then you try to lock the second mutex. In procedure 2, thread 2 is actually going to do things in a reverse order. Okay? You're going to lock mutex 2 first, and then you're going to try to lock mutex 1. Okay? So again, think about a scenario where you have these two things that are running in two different processors. Okay? So both of them come in at the same time. Right? This guy is going to lock mutex 1. On the second processor, it's going to lock mutex 2. No problem. They can be done in parallel. Okay? Now this guy will try to execute the next statement. It will try to lock mutex 2. Well, mutex 2 is locked by thread 2, so this guy is not going to get a lock. Okay, thread 2, what it will do is it will try to lock mutex number 1, and mutex number 1 is held by thread 1, so this guy is going to get blocked. Okay, these two threads, right, this mutex lock will not return until the mutex become available or are given to this thread. All right, so if both of them are getting blocked over here, is any one of them going to progress? Okay, none of them is going to make any more progress, and they're going to be stuck here forever. All right, there's absolutely no progress, right? So this is called a deadlock. Okay, and both threads, there's really no way to actually break a deadlock. Okay, the only thing that you can do is that if you have another thread, you can call exit. Right? Otherwise, these two threads, right? Because when this guy, in order for this thread to execute the next statement, it has to return from this. And in order for it to return from this, it has to have the mutex number 2 lock in its hand. Right? The only way that it can, that it can have mutex 2 lock in its hand is if thread 2 release that mutex number 2. And the only way thread 2 can release that mutex number 2 is with this statement over here when it unlocks mutex number 2. But this thread never gets there. Okay, so this is called, some people call it the deadly embrace, basically, we're stuck. Okay, so you can actually draw this as a graph. So this is some kind of graph representation, right? Over here, the arrow meaning that, that you are waiting for something. And if you have some arrow points to you, that means that you have some resources held in your hand. Okay, so in this case, thread number 1 will if it's right here, it will hold mutex 1 in its hand, right? So there's an arrow over here. And thread number 1 is going to wait for mutex 2. thread number 2 over here held mutex number 2 and it's wait for mutex 1. Okay, now you have a circular situation, right? Here's a circular loop, and none of them is going to release anything, until it gets the other lock. Okay, so you're going to end up with a deadlock situation. Okay, so pretty much anytime when you see a deadlock, you can analyze the thread and the stuff that they are held, and you can draw this picture, and you're going to realize that there's always going to be a cycle. Okay, so if you look at things that are executing and the resources they're using, and you construct this graph, you're guaranteed to see a cycle. Okay, and that's when you're going to end up with a deadlock. Actually, deadlock is a really, really old problem. Since the day people starting to program, multi-threaded program or multi-process program, they run into deadlocks. Okay, so this problem has been studied to death. So it will actually realize that all these 4 conditions must be met in order for a deadlock to be possible. Okay, that means that if you are in a deadlock situation, okay, then you try to check all these 4 conditions. All these 4 must be true. Okay, but on the other hand, if all these 4 conditions are true at some instance of time, does it guarantee that you're going to end up with a deadlock? The answer will be no, because deadlock is basically, it's a race condition that it depends on the timing of the execution of these threads. Okay, so if you know that you're already in a deadlock state, then all these 4 are true. Okay, and if all these 4 are true, you don't know whether something is going to happen or not. All right, so what are these 4 conditions? One is the resource has to be bounded. There has to be a finite number of resources, because if there's infinite number of resources, then whenever one thread wants to ask for something, it will just get a brand new resource. If you get a brand new resource, then it doesn't have to wait for it. Okay? So there has to be a finite number of resources that these threads are waiting for. Okay? Resource has to be bounded. The second one is that the way the thread is going to access these resources, they just don't go ahead and access it. They have to go wait for it. Okay, so you have to require that the thread needs to be waiting for a resource. And how do you really wait for something? Okay, so how do you wait in a supermarket? How do you wait for at a bank? Right, you get into a line and you wait for it. Okay, so the way these threads are going to wait for something is also they're going to get into a line, and inside this line, in a deadlock, they're stuck in that line forever. Okay, so all these threads are required to have some kind of a waiting going on. Okay, number 3, there's no preemption. Okay, the resources cannot be revoked from a thread, right? So one thing that I can solve the deadlock problem is that if I have a thread over here is waiting, is waiting for a resource and is holding another resource, okay, I can have some kind of an operating system over here and come and say, we don't have this anymore. All right, if you go back to the previous picture, right, if I can do that, okay, this guy is holding mutex 1. If I all of a sudden I say you don't have it anymore, I can give mutex 1 to thread 2, then thread 2 will starting to proceed, and eventually thread 2 will free up all the resources, and then thread 1 can proceed. Wouldn't that be nice? Okay, so that's called preemption. You hold something, but somehow another entity come and take it away from you. Okay, but what happened to thread 1 right now? If thread 1 thinks that it has held mutex number 1 because of the way this program is written. Okay, when it tries to execute this particular code, it thinks that it has thread 1 and thread 2 locked. Okay, so you better not take away mutex number 1 from thread 1, because otherwise thread 1 will get confused. Okay, so even though this is a nice concept, if you can revoke the resource from a particular thread, but you don't really know what you need to do for this particular thread, because this thread, when it starts to execute, it will assume that it has that resource. All right, so revocation is actually not a good idea. Okay, be very careful when you try to revoke access, of a particular, thread. Okay, so the requirement over here is that, that you cannot have preemption. If you have preemption, then you can just take away, a resource held by threads. You can make it available to other threads, and therefore you have no deadlock. All right. Number 4 is that you have to have a circular way. If you draw that picture, you're going to find a cycle somewhere. All right, so given that we know that when a deadlock happens, all these 4 things must be true, what can we do about that? Okay, one thing that we can do is that if we have a way to guarantee that one of these conditions is never true, okay, just pick one. Okay, if you pick one of them, you say this condition can never be true, can you ever have a deadlock? Okay, basically you have just prevented deadlock, right? Because you know that if a deadlock has to happen, then all these 4 conditions must be true. So if one of them can never be true, then you can never have a deadlock. All right, so it turns out that you can actually prevent deadlock, and that's the kind of trick we're going to learn is how to prevent deadlocks. Okay, deadlock is actually a pretty complicated subject. You can spend many lectures on just about deadlocks. All right, so when we write a program, we're going to end up with a deadlock. It's actually be considered a deadlock. It's a programming bug because you should program your code so that it doesn't deadlock, right? And the deadlock is, again, it's done because of a race condition, and your code should never have a race condition. Okay, so therefore deadlock should not occur. Okay, it's tricky to figure out deadlock. It's because it's a race condition. So it happens sometimes, and sometimes it doesn't happen, right? You run your code 99 times, there's no deadlock. The 100th time, it deadlocks, and that's the time the grader is grading your assignment, right? So that's the time you're going to deadlock, right? So, it makes it very difficult to debug, okay? The hard thing to do is for some other software to detect that deadlock has occurred, okay? When you start coding warm-up number 2, you might see a message from the pthread library that says, oh, I think there's a deadlock. Okay, so there's actually a way to detect deadlock. Okay, so what the pthread library tells you is that, hey, maybe you should fix your code. Okay, the problem with detecting deadlock is once you detect it, what are you going to do with it, right? Are you supposed to kill a thread? Okay, you really can't just go ahead and kill a thread. Operating system shouldn't just kill threads because you have these threads that you wrote inside the process. These threads are supposed to work together. If you kill one of the threads, then everything's going to become really weird. Okay, so the problem with deadlock detection is that the only thing that you can do once you detect deadlock is that you can kill the process, okay? Because there's no point killing a single thread, right? So that's not good. That's the same thing as pressing Control-C on your program, right? That also killed the process. So this is, and also detection deadlock is also not so easy, okay? It might be very, very resource intensive for some other process or other thread try to figure out that a deadlock has actually occurred. What's much easier is to prevent deadlock by making sure that one of those conditions can never happen. All right? Then, that's a much easier way to go. So again, we're not going to cover too much about deadlock prevention. All right? Some of the examples of deadlock prevention are, you can try to attack condition number 4 to make sure that there's no circular weight. Okay? So here's an example. It's called locking hierarchy. Right? Over here, there's gazillion mutexes. So when you have that many mutex, you're going to be in trouble because your program becomes very, very difficult to write. Okay, so in this way, we have a lot of mutex. Okay, we want to make sure that we don't deadlock. One thing that we can do is that we can assign some sort of a hierarchy to all our mutex. We can organize them into levels in this particular approach. For example, we're going to say, this one is called level 1, level 2, level 3, and level 4. Okay, at each one of them, at every level, there's a bunch of mutexes. And we're going to follow the rule that you must not try locking a mutex at level I if you're already holding a mutex as a level J if I is less than J. Okay, otherwise it's okay. All right, so if you apply this, right, you can take a look at this example. If I'm holding mutex at level 2 and 3, if I'm holding level 2 and 3, am I allowed to wait for a mutex at level 3? Okay, right? You can only wait for something if something is bigger. Otherwise, you're not allowed to wait for it. Okay, so if you're holding these two mutex, then you cannot wait for any of these guys. You can only wait for something in 4 and beyond. Okay, so why would this work? Right, so that means that you're holding these two mutex. The next mutex that you're going to lock, or you're going to wait for it, is going to be something below it. Okay, so you're holding these two mutex and you're waiting for another mutex over here. And once you have number 4, then the only thing that you can wait is for something that's even lower with a larger value. All right, so in this way, when you construct your graph, all the arrow points in one direction. Can you ever have a cycle if all the arrow point in one direction? Right, so you have one thread waiting for something like this. Another thread has grabbed these guys, and they're all waiting like in this direction. Okay, so you can never have an arrow that actually go up. Okay, if you can organize things in this hierarchical way, right, 1, 2, 3, 4, and stuff like that. If you draw the resource graph, one resource waiting for another one, all the arrow are pointing downwards, so therefore you can never have a cycle. Okay, so this is the easy way to make sure that that you can never deadlock. Okay, so I guess over here is the picture, right? You have 2 and 3 locked. According to that rule, you cannot wait for 1, 2, or 3. You can only wait for stuff 4, 5, and 6 and beyond. Okay? All right, what if you cannot organize your mutex in such a strict order for deadlock detection? Okay, so this only works if you can assign levels to your mutex. What if you can't do it, right? Then this whole approach go out the window. You got to take a different approach. Okay? All right, here's another example of a different approach. This is called conditional locking. pthread actually provide you a way. So the previous approach, you can use pthread, you can use anything, right? You as a programmer, every mutex you have to assign at a level. Okay? This one actually is something that pthreads provides. It's called conditional locking. Thread 1's code is exactly the same as before. Thread 2 is going to be a little nicer. What it will try to do, it will try to lock a mutex. Okay? So it will first lock mutex number 2. Okay? And then it will try to lock mutex number 1. Okay? So the problem with the previous case is that when it tried to lock for the mutex 1, it basically get on the queue and wait for mutex number 1. Okay? And it can actually wait for that forever. Right? So that's why you end up with a deadlock. Over here, what if you just say that I'm going to try to lock mutex number 1? If it turns out that I cannot lock mutex number 1, I'm going to give up mutex number 2. All right? So this code says, I'm going to stay in the input loop over here. I'm going to lock mutex number 2. Then I'm going to try to lock mutex number 1. If I cannot lock mutex number 1, I'm going to unlock mutex number 2. All right? Then I'm going to go back over here. I just unlocked mutex number 2. I'm going to lock it again. I'm going to come back and lock mutex number 2. I'm going to try to lock mutex number 1 again. If I can't get it, I'm going to give up mutex number 2, and I'm going to come back over here. All right? So this one, I'm going to actually stay in the loop, for a long time. Okay? Because eventually, what I'm going to do is that I'm going to lock mutex number 2, and I'm going to try to lock mutex number 1, and this time I'm successful. All right? And why would it be successful? Because thread 1 will not wait forever anymore, right? Because thread 2 will give up mutex number 2, so thread 1 will continue to execute even though you were at a condition where previously it's going to deadlock. Okay? So thread 1 is going to execute. This might take a long time, but eventually thread 1 will unlock mutex number 2 and lock mutex number 1, and then this guy, if it can actually lock mutex number 1, then it will call break. It will break out an infinite loop. At this point, thread 2 will have both mutex 1 and 2 locked in its hand. Right? And then it can do whatever it needs, and then eventually unlock mutex 1 and 2. All right, so this one is, you can actually also make sure that one of the conditions that specify, one of those 4 conditions never occur by giving up a mutex and not just wait for it. All right? Okay, and there are other ways to do, so you can actually find some other textbooks, that just talk about mutex in, a single chapter, talk about deadlocks in a single chapter. There's the dining philosopher problem. There are tons of different versions of deadlock problems, and we're really not going to get too much into it. All right? Okay, so when you wait for a mutex, right, we're going to look at a little more detail. The implementation of mutex, every mutex actually has an associated queue that goes with it. Okay, so this particular picture says that this is actually my mutex implementation. Okay, the mutex has a variable called lock. Okay, L-O-C-K. That means that whether the mutex is owned by somebody or not. Okay, the other thing that mutex has is has a first come first serve or first in first out queue, just like the one that you implement in warm-up number 1. It's basically a simple list. Okay, so the idea over here is that if you want to implement mutex lock, okay, how is mutex lock getting implemented, right? So what you need to do is that when you call this particular function, you're going to call the implementation of pthread mutex lock. What it will do is that for this mutex, it will see if the lock is being locked by some thread or not. If it's not being locked by some thread, then you get the lock. Okay? When you get the lock, what I'm going to do is I'm going to draw this picture to say that you are inside this box, which means that you can execute any of the critical sections. Because at that point, you have the mutex, right? So this is like the key that you grab it, and now you're inside the safe. You can do whatever you want. Okay? So this one, I'm going to actually call it a sync. I guess this is my own terminology, because I'm going to refer to this box over and over again. I'm going to call this a synchronization box. Okay? And only one thread can be inside the synchronization box at a time, and that thread is the one that has the mutex locked. Okay? So If the lock variable is equal to false, then when you call p-thread mutex lock, you grab the lock and you are inside the synchronization box. You don't actually get on the mutex queue. Okay? But if you are another thread, you call p-thread mutex lock, and the lock is being owned by another thread. That means that there's one guy inside the safe. Okay, so therefore your thread has to wait for it. Okay, so how do you wait for it, right? So what you do is that your thread is actually get queued up onto this mutex queue. Okay, the other way to think about it is that this thread has a thread control block. The thread control block or the thread ID can be added into this mutex queue. Okay, and that thread that just called this particular function becomes suspended. It's no longer running inside the CPU. It gives up the processor and it's waiting in here inside the mutex queue. All right, so conceptually you can think about it, right? Every thread they are somewhere, okay? They're either executing inside the CPU, right? Or they're waiting somewhere inside the queue, or they could be inside the synchronization box, but if they're inside the synchronization box, they're executing code, so therefore they're inside the CPU. Okay, so every thread, with respect to this particular mutex, it can be only at 3 places. Then can be either inside the synchronization box, executing code, be inside the CPU, or they're waiting on this mutex queue. That means that they're suspended and they're waiting for something, or they could be outside the box. Okay, so or outside this entire thing. When they're outside, then could be doing something else, running in the CPU or not, waiting for something else. All right, so every thread can be either outside, in the queue, or inside the synchronization box. All right? Okay, and when you get on this queue, okay, if the guy that's running inside the synchronization box, if that guy never give up the processor, okay, there's going to be a problem, right? Basically, you're going to wait in that queue forever. All right, so usually what happens is that if you're executing inside the synchronization box, you're going to pick a critical section to execute, or you're going to execute all of them. But eventually, when you're done, you have to do the unlock, and then you get out of the synchronization box. Okay, when you get out, do you get back into the mutex queue? No, you are only on the mutex queue if you're waiting for the mutex to be unlocked. Okay, so if you are inside here, if you finish, you get out of the box, and then you unlock the mutex. Okay, so what happens is that when this thread called pthread mutex unlock, what happens? Okay, when you call pthread mutex unlock, the implementation of pthread mutex unlock, that implementation must look at this queue to see if this queue is empty. Okay, if the queue is empty, then you unlock the mutex and you're done. Okay, if the queue is not empty, the implementation of pthread mutex unlock must remove the head thread out of this queue and make it go inside the synchronization box. Right? Because the question over here is that if you're waiting for the mutex queue, when do you get inside the synchronization box? Okay, so actually it's when the other thread called pthread mutex unlock, that's when you get into the synchronization box. Okay, but actually you don't really get into the inside there right away. What happens is that you're going to be removed from the mutex queue and you're going to be ready to run inside the CPU. The CPU is currently doing what? Well, it's serving the thread that just called pthread mutex unlock. Right, so that thread is going to call pthread mutex unlock. It's going to execute the next instruction after that. Okay, so you have one thread that's running in the CPU. Okay, so the implementation of this unlock will simply move one of these threads from the mutex queue and make it ready to run, waiting for the CPU to become available. Okay, so they actually move this thread outside temporarily, and next time when this thread is ready to run, it will come and start running inside the synchronization box. All right, so this little timing is kind of important. Okay, that when a thread becomes ready to run, it's actually because the other thread called pthread mutex unlock. All right, so mutex is very, very simple. Okay, it's necessary when shared data are being modified. Okay, although there are cases where using a mutex is an overkill. Okay, if you have a bunch of data that you try to modify, you can use one mutex to protect them. So if you want to access any of these data, you lock the mutex. Okay, but turns out that you don't really have to lock the mutex, because what if so here are two cases where it might be overkill to use a mutex to protect all that resources. Okay, one is, what if the threads, they don't really interfere with one another most of the time? Okay, if you think about, here's a bunch of resources that you are, so here's resource 1, resource 2, resource 3, right? The resource could be a linked list, could be some other kind of data structure. You're using one mutex to protect it. Okay, what if I have one thread that want to access this resource, while another thread want to access this resource? Should I allow them to go ahead and modify, these data independently? Sure, right? Because they don't have any interference. And it's a bad programming style to have one mutex to protect everything all in one shot. Okay? So that's one condition. Using a single mutex is an overkill. Okay? Or what if some thread just want to read a piece of data? Okay? Again, you use one mutex to protect all these resources. I have one thread want to read R1, another thread want to read R1, another thread want to read R1. They all just want to read it. They don't want to change it. None of them want to write to it. Should I let them all go ahead and read it? Sure, right? Okay, but if I use a single mutex, then that means that only one of them can read it at a time. Okay, then you're going to have bad performance. All right, so now basically we're going to see things that are a little beyond mutex, try to have a little better performance because, these two condition 1 or 2 can actually happen. Okay, we're going to look at number 1 first, and I'm going to look at number 2, and they actually have a different kind of solutions. Okay, and then we're going to look at another case. It's called barrier synchronization. So we're going to see 3 different ways to deal with these 3 different situations. All right, first we're going to look at number 1. Number 1, this is called the producer-consumer problem. Okay, you're going to use the mutex to protect a circular buffer. Okay, so here's a circular buffer. So the idea over here is that, the circular buffer is an array of elements, so it's an array of resources. Okay, and you're going to have the producer trying to write data into, these array elements. Okay, while the consumer try to process data from the array elements. Okay, in this case, we're going to sort of look at them as a conveyor belt, right? So this is, this picture sort of make it look like a conveyor belt. The objects are moving over here. The producer is putting stuff on the conveyor belt, and the consumer is picking data off the conveyor belt. Okay, is there any conflict between the producer and the consumer? Right, in this picture, the producer always puts stuff right here while the conveyor belt move, sort of move to the left. Okay, and the consumer always pick up stuff from here, the stuff that's right underneath it. Then the producer and the consumer, they never have any conflicts. Okay, so therefore we don't really need a mutex to protect that. Okay, using a mutex to protect this entire data structure is a big overkill. All right, so certainly in a conveyor belt situation, right, if the conveyor belt, we actually have a circular buffer. Once, these things go off the end, they're going to come back over here so that, so that they can be continued, these buffer space can be reused. All right, so that's if we have a conveyor belt situation. So what's a conveyor belt, right? A conveyor belt is where the producers produce at a fixed rate and the consumer is consuming at a fixed rate, and they are actually at exactly the same rate. Okay, so what if the producer is a little faster and the consumer is a little slower? Okay, if the producer is a little faster, then what happens is that you can think about this belt is actually going to slow down. Okay, so the producer is going to put stuff onto these array elements one at a time, but eventually every element in the array is going to be full, right? Because the consumer is slower. Okay, so eventually everything is going to be full and the consumer is slowly taking stuff off. Right? We can think about the extreme case when the consumer is really slow, so the producer is going to put stuff all over the conveyor belt, and then at that point, the producer has to stop, right? Because if you don't stop the producer is going to write into this memory location, and it's going to corrupt the consumer. Okay? So therefore, this is condition 1 that we talk about. Only once in a while, the producer and the consumer needs to be synchronized, because only at that point, they're accessing the same location. If they are not accessing the same location, they can actually do this in parallel. Similarly, if you have a slow producer and a fast consumer, right, the producer is producing data right into this pink area over here. The consumer is really fast. It process, and now the consumer is ready to process this memory location. Should the consumer allowed to process? No, because the producer is actually writing data into this data structure, so this data structure might be inconsistent. Right? So therefore, the consumer is not allowed to access this data structure. Again, they need synchronized access to this particular memory location. All right, so in that case, we need to only synchronize when the producer and the consumer might be working at the same memory location. Right? Otherwise, they're actually allowed to proceed in parallel. So the solution for this, you know, is a little, to describe the solution, we're going to introduce some additional notations. Okay, so we're gonna introduce another notation. This notation is called guarded command. The guarded command was invented in the 1970s, and it's Dijkstra. People who have taken CS 570 must be familiar with the Dijkstra algorithm. The person who invented Dijkstra algorithm also invented this language called guarded command. Okay, we can use guarded command to describe parallelism. Okay, and we're going to use this particular notation to describe what is allowed to happen, what is not allowed to happen. So, and then we can write code using, you know, this particular language. Okay, so hopefully that will make the code smaller and easier to understand. Okay, so we're going to introduce this language first, so you can understand what is supposed, you know, the meaning of this language, and then we're going to see how they can be implemented using p-threads. All right, and then we can also sort of, you know, see the code for implementing all these kind of p-threads, you know, primitive for handling this. All right, so this guarded command, this particular syntax, it starts with a keyword. This keyword is when. It's not if, it's not while, it's when. Okay, so over here is the little note. For example, so for the exams, you need to know how to write pseudocode in the language of guarded commands. Okay, so you have to write things in this particular form. All right, so again, this one, okay, very simple. There's a keyword called when, and then in parentheses, followed by something called the guard. And guard is a Boolean predicate. Okay, it's like if then else, right? If then else, in the parentheses, there's a condition, evaluates a true or false, nothing in between. Okay, same thing over here, but we call it a guard. Okay, guard is a Boolean expression, evaluates to true or false. Okay, followed by square brackets. Okay, the square bracket, inside the square bracket, there are a bunch of statements, and the statements are called command sequence. All right, so the guarded command just have these three parts. The keyword when, followed by guard, and then followed by a command sequence. Okay, so this means that the command sequence can be executed at any time when the guard is evaluated to be true. Okay, so so this guard is a little tricky, right? Because now we talk about multi-threaded environment, okay, where the guard is a expression, right? If then else, okay, you say if, you know, A is greater than 3, B is less than 5, and C is greater than D. Okay, the guard is something that evaluates to be true or false. It can be a very, very complicated expression. Okay, so if you think about a variable A, B, C, D, right? So this can involve A, B, C, and D, and A, B, and C, and D, they are variables that are being changed by 4 different threads. Okay, thread A is changing A, thread B is changing B, thread C is changing C, and thread D is changing D. And we have a guard that involves all these variables. A is greater than 7, B is less than 5, and C is greater than D. Okay, when this condition just happened to be true, right, we can be running 4 different processors. All these things are going crazy. At the instance of time, all these conditions have become true. When the guard is evaluated to be true, we are allowed to execute this command sequence. Okay, and this command sequence is going to be executed atomically. Okay, atomically means that it's executing without interruption. Okay, so that means that when this guard is true and we're going to execute this command sequence, all these things, if the guard is true, evaluating the guard and executing the command sequence is one operation. Okay, it's considered to be one operation. It's atomic, that means that the atom cannot be broken into, you know, multiple parts. So this execution has no interruption. All right, so when you write things in this way, it means that when the guard is true and you're evaluating that guard, and if you evaluate the guard to be true, at that point you can actually execute a command sequence, and all can be done in one atomic operation. Okay, an atomic operation, how long does it take for an atomic operation to execute? Well, it can be a very long time, but if you write things in this particular way, that means that there's no interference from any other threads. So it's as if this atomic operation is executing in 0 time. It's executed instantaneously. All right, and we're writing pseudocode, right? How long does it take to execute pseudocode? It only executes in your head, so it takes, you know, only a moment to execute that. All right, so please make sure you understand, you know, what's being described over here, okay? The last sentence is very important. Evaluating the guard and executing the command sequence altogether is an atomic operation if the guard is true. Okay, and also if the guard is true, you don't have to do this. You can do this. Right over here it says can be executed. You're not required to do it. Okay, but when you decide to do it, then at the the evaluation of the guard and executing all the statements is one atomic operation. Okay, you shouldn't do something like evaluate the guard is true. I'm going to wait for other thread to execute, and then I'm going to execute a command sequence. That is not allowed. Okay, when you evaluate the guard to be true, if you decide to execute a command sequence, you must execute right at that time, and without any interference. All right, so that's the meaning of this particular guard command. Okay, so how are you going to use it? Okay, we're going to use that to define, to write some subroutines. Okay, so for other primitives to use. So one of the things that we can use the guard command to describe is something called semaphores. Okay, you probably have dealt with semaphores if you have written Java program and stuff like that. If you write some C++ program, maybe you have dealt with semaphores. Okay, a semaphore is something, it's an integer. Okay, a semaphore S is a non-negative integer. It can go all the way to 0, but it can never go negative, on which there are exactly two operations defined by two guard commands. Okay, so instead of to describe exactly what a semaphore does, we're going to use the language we just learned to describe these two operations. Okay, a semaphore is described by the operations. There are two operations. One is called P, the other one is called V. I guess Dijkstra was Dutch, so P and V are Dutch words that mean something in Dutch. But these days, we don't, people don't even know what it stands for. Okay, so P is the decrement operator, and then V is the increment operator. Okay, so P of S, right? S is a semaphore. It's a non-negative integer. Okay, it's an operation can be written as the following, guard command. Okay, so P of S is equal to, right? Or if you think about function declaration, this is the function declaration. This is the function implementation. All right, so the implementation of the P operation is when S is greater than 0, S decrement S. Okay, so if S is not greater than 0, right, which means what? S must be equal to 0, right, because S is a semaphore, it's an integer, it can only be 0 or bigger, it can never be negative. So when it's not greater than 0, then it must be equal to 0. Okay, so if S is equal to 0, this operation is blocked forever. Okay, or P of S is going to get blocked forever if S is equal to 0. Okay, eventually when X becomes greater than 0, then you can execute the evaluation of S greater than 0 and decrement S at the same time. All right, atomically, right? The second operation is called the V operation. The V doesn't have a when part. Okay, so apparently, when you try to, increment the semaphore, you can increment at any time. Okay, so over here, S is equal to S plus 1, but we put it in the square bracket to say that S equal to S plus 1 needs to be executed atomically, right? And why is that? Right, we saw that already before, right? We have two threads, X equal to X plus 1. You have two threads both doing X equal to X plus 1. It might not have the desired effect. Okay, so therefore, for the X equal to X plus 1, we know they compile into 3 machine instructions. All these 3 machine instructions need to be locked together, and there should be no interference from another thread when X equal to X plus 1 is getting executed. All right, so that's why this has to be inside a square bracket, right? Otherwise, you might interleave to another thread after you load X into register R1. Okay? There are no other means for manipulating the value of S other than initializing S. Okay, so the semaphore is only defined by these two operations, right? So now we're going to see how it's being used. Okay, so one is to use the semaphore. It's called a binary semaphore. So you declare a semaphore S, initialize the value equal to 1. Okay, so at this point, there's no thread, using it, right? So therefore, you're safe to set it to 1. Okay, and now what you can do is that you can write a function to access the semaphore one at a time. Okay, so in this case, what you would do is that in the beginning, you would do P of S, you would decrement the semaphore, and in the end, you would increment the semaphore. Okay, and now imagine you have 100 threads, they all call one at a time. Okay, what's going to happen, right? The first thread that gets here, P of S, okay, it's going to execute a code, this code, right? The code is right here. Is S greater than 0? Yes, right? Because at that point, S is equal to 1. It's going to decrement the semaphore in an atomic fashion. Okay? So the first thread is going to start executing right here. Okay, if at that point you switch to run another thread, okay, the other thread is going to run. The other thread is also right here at P of S, right? S is equal to 0, so the other thread is going to block. All the other 99 threads, they will all block at P of S. Okay, the first thread continue to execute. Eventually, when it finishes, it's gonna call V of S. V of S increment S to 1. All right. At this point, the first thread continue to execute. Okay. And eventually, some other thread gets to execute. When another thread execute, then the other thread is gonna say, oh, S is not equal to 0 anymore. So the next thread that's executing the P statement, that's the one that's gonna get in. All right, and then all the other thread, if it gets a chance to run, it won't be able to get in because S is equal to 0. All right, so even in a multiprocessor system where you have 100 processors, you're going to make sure that this code is executed one at a time. Right, that's what this function is called, one at a time. Okay, and if you look at the semaphore value go from 1 to 0 to 1 to 0 to 1 to 0, 1 to 0. Right, so this is called a binary semaphore. Okay, and this part is actually looks just like the critical section that we saw before. Okay, where's the mutex? Well, there's no mutex. We're going to use a semaphore instead of a mutex, right? So this way, using this code, using a semaphore, so this is exactly like pthread mutex lock, and this one looks exactly like pthread mutex unlock. There's really no difference between the semaphore and the mutex. Okay, so this example, there's actually no difference. Okay, so when you're using a binary semaphore, this code and this code is doing exactly the same thing. Okay. What about we do this? This is called n at a time. Okay. So what you do is they initialize the semaphore equal to n. Okay. And now you have, let's say n is equal to 7 or something like that. All right. If you have 100 threads calling this function, okay, how many threads can be in here at a time? Right. 7. Right. Because the first one comes in over here, decrement 7 to 6. Second one, 6 to 5, 5 to 4, all the way to 0. So then you have 7 threads that are executing over here concurrently. Okay, and then all the other 93 threads, they're going to get blocked right here, right? When the first thread get out, another thread going to come in. Okay, so this is called n at a time, right? So if you use one, mutex, then it doesn't really work this way. Okay, so the main difference between semaphore and mutex is that if a thread locks the mutex, it's holding a lock, therefore nothing else can get, can get in. And the other thing is that it must be that thread that unlocks it. Okay, if you have a thread locks the mutex, who's allowed to unlock it? Well, only that thread, right? Because that thread is in the critical section. When it's done, it's need to unlock the mutex. Semaphore is actually not the case. Okay, oftentimes when you see semaphore code, like in Java or C++, you're probably going to see one thread, decrement one semaphore, and it's going to increment another semaphore. All right, we're going to see that in the next example. So one of the main difference in a semaphore is that the way it's going to be used is not going to use it this way. It's going to use it in a different way. All right, and hopefully the other way is going to give us better parallelism in these threads. All right, so that's what we're going to use to look at this example. Again, we're going to go back with the producer-consumer example. We're going to have 2 semaphores. One is called empty, that tell you the number of empty slots. And the other one is going to call occupy, is going to show you the number of occupied spots. All right, so we're going to pretend that B is equal to 8. Okay, so we're going to start with the shared resource where there are 8 memory locations. Okay, and then the producer is going to put data into these memory locations, and the consumer is going to take stuff out. Right, so in this case, you can actually have a parallelism of kind of like 8. Okay, but we're only going to use 2 threads. One is the producer's thread, and the other one is going to be the consumer thread. Okay, this is the producer's thread, this is the consumer thread. And inside this code, we're going to call P on one semaphore, and the V is on a different semaphore. All right, so this is the normal usage of the semaphore, where the thread do the P and the V actually on different semaphores. Okay, the consumer is going to do P and V on different semaphores again. All right, so let's see how this code works. Okay, we're going to run this as an example. B is equal to 8, right? So initially, empty is going to be equal to 8, occupy equal to 0. Next in and next out tell you where to, the next in is basically the producer, what's the next location to put data in. And the next out is where the consumer is going to take data out. All right? In the beginning, next in and next out is all going to be 0, so you're going to have a conflict at the beginning. right? So in the beginning, you got to make sure only the producer can produce and the consumer cannot consume because there's no data to consume. Okay, so over here, what's going to come in is that the producer is going to try to decrement the empty semaphore. Okay, so unless the semaphore P empty, the empty semaphore is equal to 0, that means that there's no empty slots left, then the producer should be blocked. As long as there are empty spots that are left in this array, then the producer is allowed to proceed. The consumer over here tried to do a P operation on occupied, right? So as long as the number of occupied slots that are bigger than 0, then the consumer is allowed to proceed. Otherwise, if there's nothing occupied, the consumer has to wait. Okay? So in the beginning, this guy is equal to 0, this guy is equal to 0, this is equal to B, this is equal to 0. Let's say that we have two processors, okay? So we can do these things in parallel. One is executing this, and the other one is executing this. This guy is going to execute P, this guy is going to execute P right here. Okay, the consumer is going to get blocked because the occupy is equal to 0. Right, so therefore the consumer is going to get blocked indefinitely until occupy become bigger than 0. Okay, the producer is allowed to proceed. Okay, so we get into the next picture, right, where the consumer thread get blocked. I'm going to use the X over here to say that this guy is blocked. This guy is going to execute P of empty. So empty is equal to 8 right now, right? Empty is equal to 8. Okay, we're going to decrement 8 equal to 7, right? And then we're going to go to the next instruction. Okay, what does the next instruction do? The next instruction says buff next in is equal to item. We're going to take this item, we're going to put into next in is equal to 0. We're going to put something in here. All right, and then next in is equal. So at this time, is the other thread allowed to execute? No, because occupy is still equal to 0, right? So the other guy is still blocked. Okay, next in is equal to next in plus 1. So we're going to change this pointer to point to right here. Okay, because next in tell the producer where to write data into. Okay, if next in equal to B, if next in equal to this guy, then next in equal to 0, right? Basically, we're going to use this as a circular buffer. So we're going to check this guy to pretend that this buffer is circular. Okay, after we do all that, we're going to V on the occupy. We're going to declare that this space now is occupied. We're going to increment the number occupied by 1. Okay, so this will allow the consumer to proceed. Okay, so in that case, the producer will continue to produce. It will return over here, and it's going to do something to produce the next item. And when the next item comes along, it's going to call this guy again. Okay, where the item becomes data that it has produced. Okay, it's going to do a P operation on empty. Now the empty is equal to 7, so it's going to go to 6. Okay, and then buff of next in, well, next in is right here. It's going to put a second piece of data over here, right? Increment next in, okay? Do the circular buffer check, okay? And then it has 2 locations that are occupied now. Okay, so you can see that if we keep allowing the producer to keep going, okay, so what it will do, the producer is going to put stuff in here over and over again, right? If all this time the consumer is not running, then it's going to be like this. Eventually, the consumer is going to get to run, okay? When the consumer run again, next time, it's going to do the P operation, continue doing the P operation, right? Because the P operation is a guarded, clause. It says when occupy is greater than 0, then decrement occupy. Okay, so when this guy run again the next time, now occupy is going to be equals to, right, this example, if I put 5 things in them, this is equal to 3, and this is going to be equal to 5. Okay, so occupy is going to be equal to 5, so therefore occupy is going to decrement into 4. Okay, item is equal to buff, next out. Item is this local variable right here. You're going to take the buffer data over here and copy into this local variable. Okay? And then next out is going to be incremented to point to here. So now the consumer is going to start taking data out of here. Okay? Do a circular buffer check. Make sure you don't fall off the end. Okay? And then you do a V on the empty spot. You basically declare that this buffer is ready to be produced again. Right? This one, the consumer said, I'm done with it. Go ahead, can write more data into it. Okay? And the way it's doing that is to increment the empty semaphore. Okay, so now the empty become 4, right? Okay, so when both the producer and the consumer are outside of these routines, then occupy plus empty is always going to be equal to 8. But when they're executing in the middle, maybe when you add them up, it's not going to be equal to 8. All right? And then what it will do is it will return item. So whoever who called consume basically is trying to take some data out of this buffer and then try to process it. Okay, so once the data is copied into this local variable and then it get copied out, right? In this case, we're not returning a pointer, we're actually returning the value, so therefore that data can be removed from the stack. All right, so now the consumer can actually come here and over again, eventually it's going to catch up with the producer, and then it will get blocked. All right, so you can see that these two threads, the producer and consumer thread, they can actually be interleaving, running on multiple processors, and this code will execute correct, all the time. Okay, they will not step on each other's toes. All right, so the slide over here, I guess what I'm doing over here is just, have an animation to go through it one step at a time. Okay, so I'm just going to skip through all of them. All right, so semaphore is an important primitive. In POSIX, they implement a mutex. They also implement a semaphore. And the way they implement semaphore is basically, use the same thing they do to use it, to implement mutex. And that can be, and they provided them using different, primitives. Okay, but as we're going to see, that semaphore can actually be implemented using mutex. Okay, or any kind of a guarded command can be implemented using mutex. All right, so for the warm-up number 2, I will actually strongly encourage you to implement the guarded command using mutex directly and not try to use semaphores. Okay, so what we're going to describe next is how to implement guarded commands, and that's what you can use to do warm-up number 2. So over here, this code shows you that, the guarded command implementation of producer and consumer, you can map it one-to-one to use samwait and sampost. Okay, just replace the P and the V with these function call, and then your code should work. Okay, so therefore, this will encourage you to write, pseudocode like this, almost, the same as C code, and in the end, take one step to convert that into, P-thread code. Okay. Okay, so the guarded command, how do you implement this, right? The guard can be complicated. It might be involve variable A, B, C, and D. Okay, the complicated expression, if the guard is A less than 7, B greater than 5, and C is less than D. Okay, and all these variables are changed by other threads simultaneously. So how do you really implement this, right? This is really messy. Okay. So we should think about these variables that get involved. They are changing continuously. They're executing in different processor. So we shouldn't allow that to happen. Okay, we got to make sure that they are, changed in a controlled way. Okay, so in order for you to implement guarded sequence correctly, you must not allow A, B, C, D to get changed at any time. You got to have a way to synchronize the changing of A, B, C, D. Okay, so by following these kind of rules, okay, that I'm going to describe next, that you can make sure that the guarded commands are actually implemented correctly. All right, so this is where, mutex and stuff like that is going to get involved. Okay, so what POSIX provide is something called condition variables so that you can implement guarded commands. Okay, so implement guarded commands, we need two things. We need mutex, and we need condition variables. So these are the original POSIX primitive for implementing synchronization. Okay, all the other fancy stuff like semaphore. We're also going to see some other stuff called readers and writers and those kind of stuff. They can all be implemented just using mutex and condition variables. All right, so these are the things that we need to stick to in warm-up 2. Okay, a condition variable what is a condition variable? It's simply a queue of threads waiting for some sort of a condition. Okay, so it's waiting for a condition to happen. This condition sometimes is called an event. Sometimes it's called a condition, sometimes it's called a notification. Okay, I guess notification you're familiar with, right? In your cell phone, you get a notification, something has happened. Okay, so you only notice that something has happened. You only be notified if you are watching for that event to get, to happen. Okay, so in order for you to get notified, you have to get on the condition variable queue. If you're on that queue waiting for something to happen, then you will see that something happens. Okay, if you are not on that queue, and when this event happens, then you might miss it. Okay, so therefore, when you try to use the condition variable, you got to make sure you get on the queue at the right time. All right, so we're going to have rules that govern how the condition variable has to be used with the mutex so that you can make sure that you never miss a condition or notification that you're supposed to observe. All right, I'm out of time today, so what I'm going to do is that I'm going to continue from this point on tomorrow when I record the separate lecture. My lecture, the separate lecture, is not going to appear on the class website, but if you go to the Dan website tomorrow, hopefully after 12 o'clock at noon, you should be able to see that there's going to be a new lecture appear in the Dan website. Okay, and please make sure you go over that entire lecture before the next lecture on Monday. All right, because I'm just going to pick up wherever the next lecture left off, starting with the Monday lecture. All right, see you.